Welcome to this explainer. I am absolutely thrilled to have you here today because, well, we're going to uncover the invisible physics that literally power almost everything in our modern world. We so often take our tech for granted, right? We just interact with screens and machines without a second thought. But just beneath the surface of our daily routines lies this absolutely fascinating, unseen realm of moving fields and energetic forces. So today, we're exploring the captivating world of electromagnetic induction. It's this fundamental principle that connects electricity and magnetism in this really beautiful, almost magical dance.
To get us started, I want you to think about a super mundane, everyday action. You're at the store, you're buying a coffee, and you swipe your credit card. Instantly, an electrical signal is processed, and your money is securely transferred. But wait, how does sliding a simple piece of plastic through a machine actually do that? Why do you have to swipe it? Why can't you just, let it sit there? Well, the answer to that question unlocks the exact same physics that powers massive generators, space shuttles, and even experimental weaponry.
Okay, let's dive into this. Notice that black strip on the back of a credit card. That strip is actually a really thin layer of magnetic material, and it has all your financial information stored entirely within its magnetic patterns. But here's the catch. The machine cannot read those patterns if the card is perfectly still. Reading that information strictly requires a swiping motion. And the physical reason that motion is absolutely necessary is due to a phenomenon called electromagnetic induction. Without motion, the magnetic fields stay totally quiet. But with motion, they speak in the language of electricity. All right, Section 1, Unlocking Faraday's Law. Motion creates electricity.
So, to truly grasp how this works, we need to travel all the way back to 1831 and meet physicist Michael Faraday. He discovered a core mechanism that honestly changed human history forever. He realized that relative motion between a magnet and a coil of wire actually generates an electromotive force, or a voltage. He proved that electricity and magnetism aren't just related, they can literally create one another through movement. But to understand Faraday's discovery, we first need to understand this vital concept known as magnetic flux. Think of magnetic flux as just a measurement of the total amount of magnetic field lines passing through a specific surface area. Imagine an invisible magnetic rain falling all around you. Now picture holding up a wire loop. The magnetic flux is simply the amount of that magnetic rain that successfully passes right through your loop. If the loop is facing the rain perfectly, boom, you get maximum flux.
Now, looking at this, you can clearly see those magnetic field lines, those blue arrows, cutting directly through that defined area. And this brings us directly to Faraday's law. It essentially states that an induced voltage in a circuit is driven by the negative change in this magnetic flux over a period of time. So the absolute crucial takeaway here is that it's not just about having magnetic rain passing through your loop, it's about how the amount of that rain is actively changing from one second to the next. Notice how moving a magnet into a coil generates a current, whereas on the right, a totally stationary setup achieves the exact same thing just by flipping a switch to interrupt a nearby current. The secret ingredient to creating power in both scenarios isn't the physical magnet itself, it's the change in the magnetic field over time. Whether you physically push a magnet or you just interrupt a current, you are changing the invisible magnetic environment. And that change, that is exactly what induces electricity. Moving on to Section 2. Nature pushes back. Lenz's law. Okay, so we know that change creates electricity, but, the universe doesn't just give away energy for free. Physicist Heinrich Lenz discovered what we might call nature's stubbornness, which is defined for us right here. But let's break down what this actually means in practice. If you take a magnet and push it into a coil of wire, you are actively increasing the magnetic flux. Well, the wire doesn't like that change, so the induced current in the wire will flow in a very specific direction to create its own magnetic field, one that physically pushes back against your hand. Think about it. If there was no pushback, you'd basically be creating electrical energy out of thin air without doing any mechanical work, which would violently break the laws of physics. And we can't have that. Now, what's really interesting about this is how vividly nature's stubbornness actually plays out. As the north pole of the bar magnet approaches, it increases the flux. To fight this, the wire loop induces a counterclockwise current. Why? Well, because a counterclockwise current turns the face of the wire loop into a north pole as well. And as we know, two north poles repel each other. So the wire loop is acting like this invisible barrier, just trying to shove the approaching magnet away to stop that change in flux. The cool thing is, you can actually predict the direction of these invisible induced currents yourself using a super simple four-step strategy. First off, figure out the direction of the applied magnetic field. Second, determine if the flux is increasing or decreasing. Third, decide the direction of the new induced field. And remember, it must oppose the change. Finally, just use the right-hand rule.
Point your thumb in the direction of the induced field, and your fingers will naturally wrap in the exact direction the electrical current is going to flow. Pretty neat, right? When we actually put Lenz's law into action, we get some wildly surprising results. Check this out. This is the famous jumping ring demonstration from MIT. So a metal ring sits over a vertical solenoid. When a massive current is suddenly turned on inside that solenoid, the magnetic flux spikes instantly. The metal ring, experiencing this huge change, induces a massive current to oppose it, essentially turning itself into an opposing magnet. The repulsive force is so violently strong that the metal ring literally fires straight up into the air. Next up, Section 3, Generating Motional EMF Scaling Up. So we've seen what happens with small coils and jumping rings, but when we start scaling up the physics, we enter the realm of motional electromotive force, or motional EMF. Take a look at this conducting rod being pulled across two metal rails through a constant magnetic field. As the rod moves to the right, the area of the circuit gets larger, which means more magnetic flux is passing through it. This changing area generates an electrical current. But because of Lenz's law, a magnetic force pushes back against the rod to the left, meaning the mechanical work you put in to physically drag that rod forward is perfectly and exactly balanced by the electrical power generated in the circuit. And finally, Section 4, Space Shuttles and Railguns' Extreme Applications. It turns out these invisible forces can be harnessed to attempt feats of unbelievable scale and power. For instance, in 1992 and again in 1996, NASA attempted to turn the space shuttle into an enormous electrical generator. Seriously. The Earth itself has a weak but massive magnetic field. So the idea was to drag a tethered satellite on a long wire through the rarefied, partially ionized atmosphere known as the ionosphere. That ionosphere acted just like stationary rails, serving as a return path to complete the circuit, while the tethers sliced through Earth's magnetic field at literal orbital speeds. And to give you an idea of the scale here, we are not talking about a short cable. This tether was designed to be 20 kilometers long. Moving at an orbital velocity of around 7.8 kilometers per second through Earth's magnetic field, physicists predicted this setup would generate a staggering 5,000-volt electromotive force. It was just an ingenious attempt to convert the shuttle's immense kinetic energy directly into electricity. Now, unfortunately, the mechanical tethers snagged and broke during the tests, but hey, the physics principles were entirely sound. And this brilliantly illustrates another extreme application, the railgun. Because instead of pulling a rod to generate electricity, what if we aggressively pump electricity in to violently push a rod? In a railgun, a massive current flows through the rails and across an armature holding a projectile. By expertly managing a rapidly decreasing magnetic field, an immense forward magnetic force is generated. This violently propels the conductive projectile forward at devastating speeds, totally without using any chemical explosives. But despite the incredible physics involved, railguns are exceptionally difficult to deploy in the real world. Generating these massive magnetic forces requires an absolutely staggering amount of electricity. We're talking about needing nearly 1 million amps of current just to produce enough energy for the railgun to be an effective tool, and that requires massive, heavy power supplies, which results in an extremely high cost of production and maintenance. And that is exactly why military adoption remains quite limited. So, we've seen how a changing magnetic flux can launch a metal ring, fight against the drag of a space shuttle, and fire a projectile. But I want to leave you with a final, provocative thought. Your brain operates using its own delicate electrical signals. If we can target these powerful laws of physics, could we use them on ourselves? Well, the answer is yes. Through a process called transcranial magnetic stimulation, doctors use rapidly varying, highly localized magnetic fields to safely induce small electrical currents inside the human brain, effectively treating disorders like severe depression. From swiping a credit card to rewiring human consciousness, the invisible magic of electromagnetic induction is literally everywhere. Thanks so much for joining me on this explainer, and hey, keep looking for the invisible forces shaping your world.